Welcome back, everyone. We are in the week 8 problem solving session of the NPTEL course Control Engineering, and week 8 is about design using Root Locus. I am Teja Golla, a fifth year research scholar working under Professor Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. So, in the last week, we have discussed about different design techniques, how we can design PPI, PD, as well as PID. And then towards the end, we have discussed about the league and lag compensation. Sanket, can you see my screen?
Yes.
Okay. Yes. So in the last week, we have discussed about the lead and lag compensation towards the end. What is lead compensation? What is lag compensation? In this today's session, basically, we'll be discussing about designing the lead as well as lag compensation using Root Locus. And in the next week, which is Monday, upcoming Monday, day after tomorrow, we'll learn how to design using frequency analysis. Basically, frequency based. Today, we'll be doing Root Locus based. So first I'll be discussing briefly about water lead and lag compensation so that I'll just quickly summarize what we have discussed, and then we'll quickly go to the design guidelines, and then I'll also show the MATLAB simulations, which is very much important because whatever we are doing, we should also have the perspective of visualizing it so that we know what is going on. So I'll show the MATLAB simulation parallelly, the time domain response, the root locus, as well as the Bode plot, so we can have the full understanding of what is going on, and it will help us to correlate what we are learning today using the MATLAB as well. So last week we have discussed about the lead as well as lag compensation. So we have basically said that lead compensation means it is phase lead. So if you forget or if you get confused, you can always remember this in this way. So let me draw lead compensation. Lead compensation. So the word lead says the phase should lead, right? So phase, how when will it lead? So the zero should come first. Zero should come first, then pole. So zero is closer to imaginary axis. Zero is closer to imaginary axis, right? And also because zero is coming, so the numerator will come first, then the denominator will come. So it acts like a derivative. So lead compensation basically acts like a derivative. And when do we use derivative, or what does derivative do? It will try to improve the response. So whenever our requirement is to improve the transient response, in that case, we'll be using lead compensation. So all of them are interlinked. So derivative means improve the transient response. Improve the transient response. So in a question, if they ask design a control so that the transient response requirements are met, like say they have given the settling time, peak overshoot, then we'll be directly using the lead compensation, because lead compensation means phase lead. Phase will lead when first the zero comes, so then only the phase will be positive. Then the pole comes, then it will be made zero again. So the zero will come first, then the pole. So zero means it is in the numerator, so it is basically acting like a derivative. So derivative means it will try to improve the transient response. So this is a logical way to remember, else we can get confused between what is lead, what is lag. So this is the way I remember, and I also hope that this will be helpful for you so that you will not get confused between lead and lag, and when to use lead, when to use lag, what is the final objective of lead compensation, and what is the final objective of the lag compensation. So now if you come to the lag compensation, it is just vice versa. Lag compensation, sorry. So lag compensation means phase lag, which means phase is negative. So first the pole will come, phase will become negative, then zero will come and bring back it to zero, which is what we have discussed in the last week as well. So here pole will come first. Pole will come first, then zero. So which means pole is closer to the origin. Sorry, or the imaginary axis to be precise. Pole is closer to imaginary axis, which means the denominator effect will come first, which means 1 by s effect will come first. So it will be the opposite of what we have written above, which means we will have the integral effect. So 1 by s effect is there. And we have discussed when we were discussing about the steady state errors, if we have type 1 system, then the step response error will be 0. So in that way, this will try to improve the steady state error. So it will improve the steady state errors. Steady state errors. So say we were given a system and we found that the steady state error requirement is not met. So they're asking us, okay, now use this compensator or design a compensator so that this is my steady state error requirement and it has to be met. So in that case, we'll be using lag compensation because it has an integral effect. Why integral effect? Because the pole will come first, then zero. So first the denominator 1 by s effect will come, then zero is placed little bit far. Okay, so why pole first? Because lag compensation phase is negative. So the pole will make sure the phase will drop to negative. Then it will come back because of the zero back to zero. So this is the overall idea of the lead compensation and lag compensation and where it will be used and how it is trying to change the transient response, improve the transient response as well as improve the steady state error. So now based on the question, we have to see which will fit and then accordingly we have to design because there are certain guidelines for lead compensation and certain guidelines for lag compensation and we have to follow them. So coming to the transfer functions. So what is the lead compensation transfer function? Lead compensation. So this is the standard that everyone follows. So Sir has also given in the lectures as well as his presentation. So let me call it GC because it's a compensator. So G of S corresponds to plant and GC of S corresponds to compensator. So it is Kc into S plus 1 by tau by S plus 1 by alpha tau. And if you see in this case, alpha is less than 1. Okay. Again, we have to see why alpha is less than 1. So without scrolling above, I'll make the same logic. Lead compensation means phase lead. So the 0 will come first, means 0 is closer to the imaginary axis and pole should be little bit far away. So if my 0 is 1 by tau, then my pole should be far away from 1 by tau. So if my alpha is less than 1, 1 by alpha is greater than 1 and that makes it the pole little bit far away from the imaginary axis than the 0 is. So that's why here alpha is less than 1. So is this clear? Is this concept clear? Sanket as well as Rohan. Someone is texted. Yes, sir. Okay. So similarly, just to separate lead as well as lag compensation, we will not be using alpha for the lag. Instead, we'll use something called beta. So GC of S is equals to Kc into S plus 1 by tau by S plus 1 by beta into tau. So now again the same logic. It says that lag compensation means it should lag. So pole will come first, which means pole should be closer to the imaginary axis. So if my 0 is 1 by tau, pole should be lesser than 1 by tau, right? So if I have 1 by beta, then beta should be greater than 1. So here beta will be greater than 1. And just so to segregate this, we will always be using these transfer functions for lead as well as lag. So there should not be any confusion between alpha as well as beta. Sir, can you please teach damping factor, Sanket? Yes, yes, yes. I'll also teach regarding the damping factor. Yeah, once I'll complete this transfer functions, I'll come to your question. So just let me finish one transfer function, which is also lead lag compensation. So lead lag compensation. Lead lag compensation will have both. And if I combine both, I'll have GC of S is equals to Kc into S plus 1 by tau. I'll call it 1 by tau 1 and S plus 1 by alpha tau 1 because both can be different, right? So S plus 1 by tau 2 into S plus 1 by beta into tau 2. So this is my overall transfer function, and here alpha is less than 1 as well as beta is greater than 1. So to avoid confusion, this is the one will always be using. So coming to your question, damping ratio, right? Damping ratio that whatever you have asked. So it is basically for the damping ratio. So it is basically for the second order systems that we consider. Say my second order system is in this way. Gc of s is equals to omega n square by s square plus 2 zeta omega n s plus omega n square. So this is the generalized expression. So this zeta is called damping ratio. So what does it do? It will dampen out the response. So if we consider a step response, let me draw the line. So if we have step response something like this, okay, and then say this is my input. So depending upon how the waveform looks like, there is a possibility that it will have some oscillations, or it will have minimal, like just it will go, or it will take a lot of time to reach. So the first case is called underdamped, underdamped, and then the red color is called critically damped, critically damped, and then the pink one is called overdamped. So based on this eta, the response will vary. So there is one more which is undamped. So in that case, we'll have pure sine oscillations. So this is undamped, which means damping is zero, which means eta is zero. So in this case, if you see, the denominator will be s square plus omega n square. So the poles are at on the imaginary axis, plus or minus j omega n. So that's why it will cause this oscillations. So the oscillations will not grow, but it will not decay either. So they are marginally stable. The whatever is the initial condition, based on that, the oscillations will keep on going. So this is how the oscillations will retain. Is that clear, Sanket? Sorry, Sanket, I'm not comfortable in Hindi, and that's why I'll be talking in English. I don't know Hindi. Okay. So yeah, so if the doubt is clear, then let us come back to the root locus design using the lead compensation. So what are the guidelines that we have to follow and how we will be doing? So yeah, say, sir, we both have control systems in Monday exam. Okay, okay. Then, like I would suggest you to cover as much as possible with your syllabus, and also go through the lectures properly. And if you have any doubts, you can always go through the YouTube videos. And I have also uploaded these recording sessions in my YouTube channel. So if there is any relevant topic that you would like to go through again, you can always go through the videos where we have solved some problems, and relevant MATLAB files also I have uploaded. So you can always cross check and then get your doubts clear. Uh, Time response I can't revise because this session is especially for root locus, whereas I have already covered the time response in the previous session. So you can go through that because that video is already uploaded, and this session is dedicatedly for the root locus. So I can't revise that because else we'll not get time for the root locus. So I'll be spending time on the root locus based design only. But time response we have already covered in the previous sessions, and they are already uploaded. So you can go through that video that is uploaded to my YouTube channel. Okay. So design using root locus. So yeah, the first point is lead compensation. So my GC of S will be KC into 1 sorry, S plus s plus 1 by tau, and then s plus 1 by alpha tau. And then we have seen that alpha is less than 1. Okay. So when will this be used? Again, we have discussed. So the second one will be, this is to improve the transient response. Transient response. So for a given system, say I have a system GC of s, and then G of s. Okay. So it's plus minus. So this is R of s. This is Y of s. Say if my compensation is just a gain k, then by plotting the root locus, if you plot the root locus of this root locus, then the desired closed loop poles, desired closed loop, I'm calling CL, poles should lie on this, should lie on the root locus, should lie on root locus. So if uh, the gain itself is sufficient, then the closed loop desired poles will be lying on the root locus. Whereas if they do not lie, then we have to check whether we will be needing lead compensation or lag compensation. And as I have told, if the question is about improving the transient response, then we'll be using the lead compensation. So then say if the gain itself is not sufficient, then we have to check. So basically, one more point here to improve the transient response. So we will also be getting the details regarding the closed loop poles. So we'll solve one problem, then it will be more clear. Closed loop poles. So then say gain is not sufficient. So if the gain is not sufficient, if gain is insufficient, then we'll go to improve the transient response. We'll be going to lead compensation. Lead compensation. Okay. So for the lead compensation, how are we going to do? So there are step-by-step guidelines. First, we'll get the poles. First, we'll get the poles and zeros. We'll get the poles and zeros. And once we get the poles and zeros, then we'll calculate the gain Kc using the calculate the gain Kc using the gain criteria. Yes. So now by following these steps, we'll be able to design and how to design these poles and zeros, how to get this. We will be follow some guidelines that sir has discussed, and I'll also tell you those details. Yeah, my YouTube channel name. Okay, let me just share you the important links. Yeah. So these are the important links that you can save it with you so that you can join this meeting, as well as you can get the access to the notes as well as my YouTube channel link. Yeah. So now using this step-by-step guidelines, let us first find out or solve one problem. So here I have given one planned transfer function g of s, which is equals to 1 by s into s plus 1. So I have told that design a controller to meet the following desired specifications. So because this is transient based specifications, we will be knowing that we have to do the lead compensation design. Okay. So first let us see, we have to follow the step by step. So the transfer function is known. First, we have to find the closed loop poles. Okay. So maximum peak overshoot is given, which can be written as 100 into e to the power minus pi zeta by square root of 1 minus zeta square. And then settling time Ts is given by 4 by zeta omega. So now we have to find the closed loop poles. So how do we calculate? The closed loop poles can be obtained as minus zeta omega n plus or minus omega n into square root of 1 minus zeta square. So from the given two MP and TS, we have to calculate the zeta as well as the omega n, right? But I have written a MATLAB code. So just to save our time, I'll explain how or what I have written in the code. So first CLC clear and closure will clear the command window as well as the workspace, and it will close any other plots. Then I have to define the transfer function. I have defined S is the transfer function that I have defined, and G is 1 by S into S plus 1, whatever we have given. And maximum peak overshoot, I have to convert into gain value, which is 10%, which means 10 by 100, so 0.1. And my settling time is given as 5 seconds. So from this MP and TS, if you calculate eta and omega n, this is the expression that you will get. So I have written a MATLAB code which will calculate the eta and omega n. So once I get eta and omega n, so my denominator polynomial will be s square plus 2 eta omega n plus omega n square. So this is the polynomial and I am finding the roots of the polynomial and then I am displaying. So let me run till this point. So if I run only this selected one, so I will get my roots as minus 0.8 plus j 1.09 I. So whatever I have calculated, let me first write the poles. So my poles, closed loop poles, which sir has denoted as SDs, minus 0.8 plus or minus j 1.09. So these are the closed loop poles. First, what I have to do is I have to check whether by just using a gain, I can get this desired closed loop poles. So how will I check? I'll plot the root locus and then I'll check whether these closed loop poles are lying on the root locus. If they lie, then I can use that gain and then I don't need any transfer function. Only simple gain will compensate my requirement. So let us go back and then let us see. So I have also used the root locus code that I have previously showed in my previous lectures. So the plot is I'm plotting in figure 1. I'm plotting the root locus of the G, which is my plan transfer function. This G 1 by S into S plus 1. And then this hold on grid on or just to set the font as well as font size. I'm using Times New Roman and 24. So now my idea is to check whether this root locus is passing through that desired pole. So the pole is minus eta omega n plus or minus omega n into square root of 1 minus eta square. So this I am marking in red color. R corresponds to red color. X corresponds to X mark. And I am putting a line width of 2. So if I run this, it will plot the root locus of the plan transfer function and also my desired closed loop poles. So let us wait until it runs. So it has run. So just let me see why it has not plot this. Okay. So my how much is my eta omega? Just a minute. This is zero point 0.8 and omega n into square root of 1 minus theta. This is 1.09. So this is above this. So that's why I think it is cutting that. Wait, I'll just close this and I'll plot again. Okay. So the root locus of G, the root locus of G is plotted. These are not in the axis, so that's why it is. Okay, hold on. I have to go hold on. Yeah. Got it. So what mistake I have done is I have not hold on. So this has to be hold on. Hold on. And here also hold on. Let us now check. It is still not plotting. So what we do is we will only plot out locus. We'll do all this. Here I have to have the folder. Okay, actually, it is clipping the scale, but as you can see, the root locus is moving on this vertical line, and my pole is lying on the 0.8 line. So basically, the root locus is not passing through the closed loop pole. So which is what I want. So the only k itself is not sufficient. So based on the root locus, I can say that only k gain is not sufficient. Gain k is not sufficient. Okay. So in case this is not sufficient, then what we have to do, then we have to actually design the compensator. And how are we going to design it? So let us check. So my transfer function gc of s is nothing but kc into s plus 1 by tau by s plus 1 by alpha tau, right? So the pole, this I can also write it as kc into s plus 0 of the compensator by 0 of the pole of the compensator s plus zc by s plus pc. So now our objective is to design this compensator so that my overall closed loop poles will pass through this. So how are we going to do this? So from the root locus, we know the gain criteria as well as the phase criteria. So how much additional phase, because it is not passing through that, first we have to check how much is the additional phase that is needed. So let me quickly draw the line. Yeah. So these will be the open loop poles, right? So the open loop poles are one is at S and one is at 0 and one is at -1. So we have one is at 0 and one is at -1. 0 and -1. And the other pole is at the desired SD is at here, right? So this is my desired SD pole. So now what I need is basically this is minus 0.8 plus or minus j 1.09, right? So if you see, I have to calculate how much additional phase I need. So that can be calculated by this. So if you calculate this distance, this is at 0.8 and the height is j 1.09. Okay. So the height is j 1.09. And then you have to calculate this gain. Okay. So let us see what problems are has selected. Yeah. So this is the problem that sir has also calculated. And then we have to see how much is the angle. So this is the figure that I'm discussing about. So you have to calculate this angle as well as this angle. So this is theta 1, this is theta 2. So you have to calculate how much theta 1 plus theta 2 is, and then see how much additional theta is needed, how much additional theta is needed to achieve phase criteria of 2n plus 1 into 180 degrees. So how much additional phase is needed to achieve this phase criteria? So first we have to calculate theta 1 and theta 2, but to avoid time I will not calculate. I'll use the theta that sir has obtained. So this is theta 1 and theta 2, which is 79.61 minus 126. And then if you see how much is the additional phase that is needed, we need an additional phase of 25.8573 degrees. So we'll be needing an additional phase of 25 point, that is called 25 point, how much is this needed? 25.8573 degrees. 8573. So I'm just avoiding the calculation to save time so that we can spend more time on the MATLAB simulation. So now this additional phase phi should be given by the compensator that we have selected. So if you see the compensator plot, yeah. So if you see the compensator plot, my compensator is lead, which means pole is far away and zero is close. Say this is my zero, this is my pole, and say my closed loop pole is somewhere here. So now this is my 5, right? This is my 5. And this is my 5. So this angle will be 5. And then I can call this angle to be theta and then this angle to be gamma. So my phi is fixed and theta is also fixed. So theta is nothing but here theta is equals to cos inverse my eta, cos inverse eta. And then my phi is also fixed, but I don't know gamma. So how to choose gamma? So the question remains how to choose gamma, because choosing my gamma will decide the transient response. So this will decide the response, right? So now how do I choose gamma? Okay, so for a given gamma, how do I calculate my zero as well as pole? So sir has given one formula. I will be ZC, PC. Sir has given one formula. I will write that formula here as well. So let me just go there. Yeah. So in lecture 2, sir has considered the same problem, and then somewhere here sir has given the formula. So this is the formula that I was discussing about. So this is PCZC, the plot that I have drawn now. And then ZC, I'll write in my notes also, so that when you refer to my notes, you can have it. And then sir said all these formulas he will provide. So it is not needed for you to remember the formula. So I'll just write the formula. You may not need to mug up because he will give the formula. Omega n into sine gamma by sine theta plus gamma. So now we'll have a MATLAB simulation and then we will see how things are changing. Okay. Then omega n PC is omega n sine gamma plus phi, sine gamma plus phi by sine theta plus phi plus gamma, sine theta plus phi plus gamma. So this is the overall poles values. So now using these pole values, let us see what we can do in the MATLAB. Okay. So coming to my lead compensation code again, we have discussed till display R. So now my phi is 25.8573, right? So if I go back, my phi is 25.8573 degrees. Okay. So now theta is cos inverse eta. So cos inverse eta, and I need it in degrees. So that's why I have to use a cos d, which will give me in degrees. And the question is whether gamma should be, what is the value of gamma? I can choose gamma to be 50. I can choose gamma to be 100. I can choose gamma to be 10. So how do you choose gamma? So we'll come back to that point a little bit later. But say I have chosen gamma to be 50. Then how do I calculate ZC as well as PC? So my ZC is omega n into into sine gamma by sine theta plus gamma, and they're in degrees. So I have to use sine d. So it will be omega n into sine d gamma by sine d theta plus gamma, and PC is omega n into sine d gamma plus phi by sine d theta plus gamma plus phi. And once we get ZC as well as PC, so once we get ZC as well as PC, from here I can say alpha is nothing but ZC by PC, right? So my alpha here is nothing but ZC by PC. So I can calculate alpha as ZC by PC, which is what I have done in the code. Alpha is ZC by PC. Okay. So now, till now, I have calculated ZC, I have calculated PC, I have calculated alpha. But the question remains how to calculate KC. So there are two questions. First is how to choose gamma, which I'll come back. Now, how to choose KC. So you know that if the closed loop pole is located here, the root locus of GC into G will pass through this point, right? So the root locus, let me add one more slide. So the root locus will pass through the closed loop hole. So which means if I calculated the magnitude of GC of S into G of S at S equal to SD, the magnitude should be 1. So let me check what will be the expression. So the expression will be K into S plus ZC by S plus PC at S equals to SD into mod of G of S at S equals to SD will be is equals to 1. So from this I can get my Kc, basically this is Kc. So Kc is nothing but 1 by mod G of S at S equals to SD into S plus PC by S plus ZC at S is equals to SD. Okay, so in this way we will be calculating Kc because this is what, this is the gain criteria. So this is what, this is our gain criteria. So it has to satisfy our gain criteria, and that 2n plus 1 into 180 degrees is the phase criteria. So it has to satisfy both the gain criteria as well as the phase criteria. So then only it will pass through that pole. Okay, then we'll come back to that. But in the meantime, how to calculate Kc? Let us quickly check it. So my Kc is the magnitude of S plus PC by mod G of S into S plus ZC, right? So which is what I have written. So this is the command to calculate that. So what is my S value? The closed loop pole, which I am getting from these roots. So from these roots, my R corresponds to the closed loop poles and R of 1 corresponds to one of them. So at this one of the point, I'm calculating the absolute value, which will give me my Kc. So if I calculate this, then I'll get my Kc. Then my Gc is denoted as Kc into S plus Zc by S plus Pc. So now I got my Gc. Now I'm also given my transfer function G. So from this, I can calculate my closed loop transfer function using this feedback command. It is a unity feedback system. So I can get my G closed loop as GCL. And my desired transfer function I can also get, which is omega n square by s square plus 2 eta omega ns plus omega n square. This is coming from the requirement. Which is the requirement? The requirement is the maximum overshoot as well as the settling time. So once we get the desired transfer function plus our closed loop transfer function, we can see whether we are able to reach the desired response or not. So here I have written the command for step response. I am calculating the time from 0 to 20, and then I am taking the data in y1 t1, and then I'm plotting this y1 t1. One is the lead compensation that we have achieved, and the other one is the desired. So I'm naming the labels as well. But before we go into this, so we have understood how to calculate the poles, how to calculate the zeros of the compensator as well as its gain. But the bottleneck is the same question. How do we choose the gamma? Because that gamma might decide our response. So I'll just show what sir has done. So first gamma sir has selected to be 15 degrees. Okay. So let me select the gamma to be 15 degrees. So I'm considering the same example what sir has considered so that you will be correlating. There will not be any confusion. Yeah, so this is the response that we got, and this is the response that sir has obtained, and both are similar. If you see, I'm just showing. So again, there is less than a minute. So if this meeting ends, kindly join back so that we can continue our discussion. So if you see, my desired response is shown in blue color, and the achieved response or the compensated response is shown by this orange color, and we can see that both are not matching. What if I increase the gamma? Whether it will have any effect? Let us see. So sir has considered 50.2. So let me consider 50.2 as my gamma. So 50.2 and see whether yes. So for gamma equals to 50.2, it is perfectly matching. So my desired response as well as whatever I'm trying to achieve, both are matching. And this is what I actually want ideally. but I have selected a random gamma of 50.2. So how do I know that it is 50.2? Or what if I go with that flow? Because I have increased gamma, my response is better. So yeah, so with that logic, if I increase my gamma, say here sir has considered gamma to be 65 degrees, and if I consider the same 65 degrees, what is going to happen? So let us use the code, and let me consider gamma to be 65 degrees and see whether the response will be improved or deteriorated. So if you see, again, it was better for gamma equals to 50 degrees, and it is not good for gamma equals to 60 degrees. It is again deviating. So the question is how to choose gamma. So I'll write the question again here. So how do we choose gamma? So how do we choose gamma? So if you see, gamma should be chosen that gamma which will maximize the alpha, maximum alpha. So let us go back and then let us see the simulation quite closely again. So we have considered three gammas, right? So one is 15, one is 50.2, one is 65. So for this gamma, let me see what is the alpha. So for this gamma, let me see what is the alpha. Gamma 15, alpha is 0.4231. So I have considered three gammas, right? So for first gamma of 15 degrees, then I have considered 50.2 degrees, then I have considered 65 degrees, if I'm not wrong. Let us see, 65, yes. So for this, I am getting 0.4231. So I was getting alpha to be 0.4231 degrees. So for this, we'll see how much is the gamma 50.2. So for gamma 50.2, how much is the alpha? Let us run. Yes. So in this case, if you see, it is matching, and let us see how much is my alpha. So my alpha is 0.6265. So in this case, my alpha has become 0.6265. So let us see. Let me go back there and then let me write. So 0.6265. 0.6265. Alpha is equals to 0.6265 degrees. And then for 65, how much is my alpha? So for gamma to be 65, how much is the alpha? So the alpha is how much in this case? 0.5987. So it has reduced again. So alpha is 0.6987. Sorry, how much? 5987, right? 5987, yeah. 5987. 0.5987 degrees. And here I got the maximum value. So this is the one I have selected. So always if I am choosing the maximum alpha and the gamma corresponding to that, that is giving me the best response close to achieve my desired response. So close to the desired response. Okay, so now once I get the desired response, then I'm happy. But how do I know maximum alpha? So what people have done is people have tried to maximize the alpha. They have calculated the alpha and then put a derivative on that alpha expression to find the gamma. So people have done the d alpha by d gamma equals to 0. So d alpha by d gamma equals to 0. And then they have calculated the gamma value. So gamma value has come to this expression. So let me see what sir has given. Gamma is 1 by 2 pi minus theta minus alpha. So this is the gamma 1 by 2 pi minus theta minus 5, right? So this is the gamma that maximizes the alpha, maximizes alpha, maximizes alpha. And then this is the gamma that we have to choose so that my response will be closer to the desired, because maximized alpha is giving me that response which is close to the desired response. So now instead of choosing random gamma, let me choose this one. So I'm commenting this out and uncommenting this, which is 0.5 minus 0.5 into 180 minus theta minus 5. So let me check how much is the alpha in this case. So this is 0.6265, and this is what is my maximum alpha. And if you see in this case, my desired response as well as the achieved response is same. So whatever is my desired response given peak overshoot as well as the settling time is perfectly matching with what I'm achieving with the lead compensation. So this is the step-by-step guidelines that we have to follow to design the overall uh, lead compensation. And I'll again summarize, but I'll also plot the root locus of the G star GC. So now what we are doing is we are plotting the root locus of the compensated system, and then we'll also put this X label, Y label along with the desired closed loop poles and see whether the root locus is now passing through these poles or not. Okay, let us quickly do that. So let me run. Yeah. So now if you see the root locus now is going in these desired poles. So just to have a quick comparison, what I will do is I'll plot the, so hold on. I'll plot the compensated as well as the uncompensated both, and then let us see. So one is G star GC and one is G without any compensation. So this is my original uncompensated plant. And if you see, just by adding a gain, it will not help to achieve the desired response because it is flowing through some random uh, line. But my desired poles are here. So by adding the compensation or the doing lead compensation, now my root locus is flowing through these desired poles, which are identified with this cross. So this is what I am trying to achieve with the lead compensation. So just to quickly summarize, I'll just summarize the design guidelines so that things will be clear for you. So I have given one question where I have not mentioned lead compensation. I have mentioned I need this desired transient requirements, and I have mentioned uh, in the previous slide, in the like previous discussion at the beginning of today's session, if I'm mentioning transient response, it means derivative effect, it means lead compensation. So I know that I might have to use lead compensation, but always first we have to check whether a gain should suffice or whether we need poles and zeros like a compensation. So first, what I have done is from the given peak overshoot as well as settling time, I have calculated my routes as well as the location, and then I have seen whether a simple gain or the root locus plot will flow through this desired pole or not. But I have seen that it is not passing, which means gain k is not sufficient, and I have to design the compensator. And for calculating the compensator, first we have to see if the root locus is flowing through this, how much angle does the original plant corresponds to? How much is the phase? Once we know that phase, then we have to see this, how much is it lacking? We have seen that phase of 25.8573 needs to be contributed by the compensator, which is the roots as well as poles of the compensator. That phi is 25.573, which is the angle between this. And then gamma is something that we have chosen so that alpha will be maximized. And then theta can be given as cos inverse gamma. So from this, we can get the ZC as well as PC. But for getting the gain, KC, we have to use the gain criteria, and then KC is given by this. So all these things are incorporated in the code. So for a given system, if you calculate phi and then substitute the phi, then you should be able to get the overall compensated design. But how do we choose gamma? I have told we have to maximize alpha, and then people have done, and this is the result that we are using. And then in my code, again, you should not use the code blindly. You should understand what we are doing. So at the beginning, I'm trying to clear the workspace as well as command window. Then I'm defining the transfer function as well as the desired specifications. And for calculating the angles, first I have to give the input phi, which I'll be calculating. And then theta and gamma are calculated accordingly. And then ZCPC, I have used the uh, comments from the formula that sir has given in the slides. I have also noted down in the notes so that you can refer to the notes. And then from the gain criteria, I can get KC. From there, I can get GC. Now I can get the closed loop transfer function as well as the desired transfer function. And then I can calculate the step response. And finally, this is my step response. If you see the desired versus achieved, it is perfectly matching. And also the root locus, if you see the original uncompensated versus the compensated, it is perfectly going through the desired pole location, and that's why the desired transient response is being achieved. So this is the overall idea of the lead compensation, where we have tried to improve the response. Now, once things are clear, if you have any doubts, you can ask me, else we can move to the lag compensation. So just to save some time, what I would like to do is I would like to copy paste things from here so that it will make my life simpler. Yeah. Okay. So once we got those, now 3, 4, and 5. Okay. Yeah. So I'll just replace what needs to be changed so that you can also correlate what has to be changed. So this will be beta tau, and we know that beta is greater than 1. And then here it is not the transient response, it is steady state. So here it is improve the steady state error. So we have to calculate KV or KA or KD, whatever they have given. So we have to calculate the steady state KV, KD, KA, whatever they are asking. And then we have to see whether a simple gain will suffice. Again, now we are not plotting the root locus because root locus is not the question, but we will see whether simple gain can achieve desired KV or not. Okay, we will see. Say if it is achieving, then my problem is solved. I will use simple gain KV, and then it is sufficient. What if gain is not sufficient? Here we will not be using lead compensation. Here we will be using lag compensation, because we have told lag compensation is to improve the steady state error, not the lead. So once we will get the poles and zeros, then we'll calculate the gain KC again using the gain criteria. But here the formula is directly given, so we will not be needing the gain KC. I'll also explain why, because it is here slightly different. So we'll get the poles and zeros, and then here also there are some formula that sir has given. We'll be using the same formulas for the 4. So once we get 4, then what is the fifth one? We'll get the overall system, and then we can check the root locus, final root locus. Check the final closed loop root locus. Okay. So let us quickly solve one problem, and then I'll also explain how do we see or solve this lag compensation. So just there is one mistake here. This is a lag compensation. How do we solve this lag compensation? Using MATLAB as well. So let us go step by step. So if we start from the first point. So here I have not told, I have told my desired specifications are both transient response as well as KB. So here there might be a catch. So what is that catch? We'll come back to it. So first point is I have given my eta to be 0.577 and my omega n to be 2.7 radians per second. So always the very first thing that we have to do is get the closed loop force, which is minus zeta omega n plus or minus omega n into square root of 1 minus zeta squared. So let us see what exactly are we going to do. Okay. So from this, if you calculate, I will get my desired closed loop poles. So this MATLAB code also I have written for the lag compensation. So I'll also be explaining the code. But if you see, I have used the same transfer function 2 by s into s plus 5 into s plus 7 and the desired specifications are 0.577, which is what we have given in the question, and 2.7. So I am calculating the roots. So if I run the code till this point, I will get the roots. So it is minus 1.5579 plus or minus j 2.205 minus 1 point, how much, minus 1.5579 plus j 2.2052. 2.2052. So this is what I got. First, again, we have to check the root locus and then check whether simple gain is fine or not. Check the root locus. Okay, we'll be checking the root locus and then see what exactly are we getting, whether simple gain is sufficient or whether we need to design the compensator using lead compensation, because here we are talking about the transient response. So let me quickly check the root locus of this G. So now my G is what? My G is 2 by, if I do ZPK of G. So this is 2 by S into S plus 5 into S plus 7. So I'll be using the same root locus, but now I don't have G into GC. So I'll be plotting this G. Along that, I'll be plotting minus eta omega and omega n into square root of 1 minus eta square. So let me do that. So if you see carefully, the poles are lying on the root locus. So the closed loop poles or the transient response that what we are trying to achieve can be obtained just by using a gain, and we don't need any compensation. So this is why it is very important to always check from the root locus, because sometimes we need not even need a compensator. A simple gain should might have been sufficient. So even if you calculate, you will be getting pole and zero on the same location. So pole and zero will get cancelled. Pole zero, basically pole zero cancellation. And then we'll be end up with the gain. So no need to do the entire practice. Instead, we'll follow the step-by-step guidelines, and then we'll see at the first instance that the root locus is passing through the desired pole location. So a simple gain K should be sufficient. So now let us see what is the gain. So if I click at that point, I can get the gain. So let me click at that point precisely. Yeah. So the gain is how much? 32.5. So I can say at around a gain of 32.5. So a gain of 32.5 is giving me the desired pole location. So which is very, very important, because so the transient response. So my transient response says, or whatever desired pole location that we are talking about, desired pole locations, this can be achieved by a gain K is equal to, how much did we get? 32.4. Oh, sorry, I think I have closed it. Let me rerun it, and then let me zoom in to that point. Yeah. So it is lying on that. So what I will be doing is I'll just calculate that point. 32.4. So because I have zoomed in, it is more accurate. So 32.4, 32.5, more or less same. So 32.4. Gain K is equals to 32.4. So now what I will do is, I have seen that the transient requirements or the desired closed loop pole locations can be achieved by this gain of 32.4. But my requirement is just not the transient. It is also about the steady state error, and KV, I am giving KV should be greater than 10. So what I will be doing is, I will be checking. So my GC of S, I got it as a simple gain, which is 32.4. And my G of S is nothing but 2 by, what is the transformation given? 2 by S into S plus 5 into S plus 7. 2 by S into S plus 5 into S plus 7. So let us see what we are getting. So we know that KV is nothing but limit S tends to 0, S into GC of S into G of S. So if you calculate, we will be getting as 32.4 divided by 5 into 7, and then there is 1 in the numerator, right? 32.4 into 2 by 5 into 7. So let us calculate how much is this. I'll use MATLAB. I don't have calculator with me. So 32.4 into 2 by 5 into 7. 5 into 7. So 1.8514. So it is lesser than 10. 1.8514. 1.8514, and it is less than 10. So this says that we are meeting the transient requirements. We are not meeting the steady state requirements. So I need to improve my steady state error. Steady state error needs to be improved. Needs to be improved. So now the question is, which compensation will we use? We have discussed we will use lag compensation. Very clear. And so now we are reaching to that point where we have realized, or we have come to a conclusion that we will be needing lag compensation because the steady state error requirement is not met. And why do we not need lead compensation? Because just by simple gain, we are able to meet the transient requirement. So there is no headache about that. Okay. Yeah. Coming to this lag compensation, what is the transfer function? GC of S is S plus S plus 1 by tau by S plus 1 by beta tau. Okay. So now if you can write this as S plus 0 by S plus 4. So now when we are designing the lag compensation, because using a simple gain is already making sure the root locus is passing through the poles. So the compensation should not contribute any additional gain, right? Or I would say that it should not contribute any more angle so that my closed loop poles are undisturbed. So this should not contribute any angle to the desired closed loop poles, which means they should be very close to each other. So very close to each other. ZC and PC should be close to each other. So only then we can say that because this is all because the gain itself is doing the duty. Gain itself is sufficient. So we will be not needing any additional gain. So also we do not need any additional phase because the root locus is already passing through the desired poles. So the additional pole and zero that we are incorporating in the system should not create any additional phase or any phase contribution, so that it will not affect the root locus plot, right? So that's why these should be very close to each other. And in this case, actually, when we are discussing about the lag compensation, how do we calculate beta? So beta is ZC by PC, right? ZC by PC. So my PC is nothing but ZC by beta. And one more thing, why we have avoided the gain K here? Because the gain K that is needed will be coming from the beta itself. Because if you substitute S equals to 0, the gain is already beta. So whatever additional gain that we'll be needing here will be coming from the beta itself. So that's why we'll not be using the gain here, because it is also not needed. Whereas in the lead compensation, we'll be needing the gain. So that's why we'll be using that. Okay. And because I have said ZC and PC should be close to each other, if I also draw the line, let me draw the line. So I use a black color. Yeah. So say my this is lag compensation. Pole is close to 0. Pole is close to 0. sorry, origin, and then followed by 0, and say this is my desired. Say this is the pole and this is the 0, very close to each other. And then say my desired pole is here. This is the closed loop pole, actually. So the angle contribution should be not much, right? So that is what we were discussing. So we consider this angle theta, or I should say phi, should be less than 5 degrees. Okay, but how do we calculate? So usually thumb rule, what we do is we will always consider ZC to be around 0.1, which is what sir has considered. And once we know ZC, then calculate PC. Then calculate PC using ZC by beta. Okay, but how do I know beta? So beta is KV desired by KV obtained. So the lag compensation is more easier to design. Why? Because I am not doing rigorous math like how lead compensation needed. So in this case here, what we are basically doing is we need additional gain to reach the or to achieve the desired KV constraint, but we don't need any additional phase contribution because that will change the pole locations. So we are trying to keep the pole and 0 as close to each other as possible. So the angle contribution, the phi, we have assumed to be less than 5 degrees. So we can't assume phi to be 0. Phi will be 0 only when pole and 0 are exactly the same place, but we don't want that. So we have assumed the angle contribution is minimal, less than 5 degrees assumption. And for this course, as far as this course is concerned, sir has considered ZC to be 0.1 and then calculated PC. PC can be calculated as ZC by beta, and beta is KV desired by KV obtained. So we'll see. Okay. So the first thing is beta is KV desired by KV of the uncompensated, I should say, uncompensated loop. Then ZC assumed to be 0.1, close to origin, and then PC will be ZC by beta. So in this way, we will calculate the lag compensation finally to get this S plus ZC by S plus PC. Okay, so this is how we will be getting the overall lag compensation. So let me just quickly browse through the code of the lag compensation. So let me close the lead compensation. So we have plotted the root locus, and then first we have seen that gain should suffice to meet the transient requirements. Point number 1. Point number 2. The eta is given. Let me just explain the code. First, we are clearing the command window workspace as well as the closing the figures, whatever are open. Then we are defining the transfer function, which is given by 2 into s into s plus 5 into s plus 7. Then the desired specifications, transient specifications are eta, omega n. From there, I have calculated the poles. And after that, I have checked the root locus, which is the step-by-step guideline. Once root locus uh, is satisfied with the given k, then I have seen that my 10 is the desired kV, and the uncompensated kV can be obtained by S into G into that 32.4, right? So whatever value that we have gotten, that is with the uncompensated, which is 1.8514. So with this 1.8514, I have realized that it is not sufficient and I need lag compensation. So this is my KV uncompensated, and again I am calculating this KV uncompensated, and then I have given the KV desired to be 10, which is coming from the input user requirement. Then how do I calculate the poles and zeros of the lag compensator? So which is what I have told. Beta is nothing but KV desired by KV uncompensated. Okay. Beta is nothing but KV desired by KV uncompensated, and ZC is considered to be 0.1, and then PC is considered to be ZC by beta. So what we ideally should be doing is once we assume ZC to be 0.1 and calculating the PC, we have to check whether the angle contribution is less than 5% or not. Once it is less than 5%, it's okay. Else we have to choose a different ZC, and then it's an iterative process. But currently, I'm not doing. So GC is S plus ZC by S plus PC. Now the closed loop transfer function can be obtained as G into GC by G closed loop. And now I'm plotting the root locus, final root locus of this G into GC as well as G. So G, what is G doing? G is simply making sure that my uncompensated loop is passing through the desired pole locations. Whereas G into GC is also supposed to pass through it. But we have additional 0 as well as pole, which will, make sure my KV is also met. So whatever I'm trying to achieve here is my G into GC is my open loop plant with some compensation so that my desired closed loop poles will not change. However, my KV or the steady state error constraints are met. So what we are trying to do is, because we know that additional GC will take care of the KV, we want to see whether this GC is altering the original root locus, because that is not supposed to happen. There may be slight change, but it should not deviate too much, and it should pass through the desired poles, which is this eta omega n. So I am plotting the root locus with and without compensation, and then checking the root locus. Yes. So if I plot the GC, this is my GC. One is 0.1 and this is 0.01851. And let us see. So if you see, there are two Bode plots. The blue color is without the compensation and the red color is with compensation. As you can see, it is not exactly passing through that, but it is very close. Why it happened? Because we have incorporated additional pole and zero, so that will alter the root locus slightly. But the additional zero and pole will take care of the steady state error. Also, since the root locus has not changed that much or drastically, my desired transient specification is also met. Okay, so this is more or less about the lag compensation. And this is my GC. So if I plot the Bode plot also to see whether it is lag or lead. So this is my GC Bode plot. And you can see it's a lag compensation because the phase is lag. And this is the magnitude plot also. Same we can do for lead lag. Same we can do for lead compensation. Again, I'll be giving all the codes so that you can play with the codes and understand what is actually happening. So let me just quickly summarize about the lead compensation. Sorry, lag compensation. Yeah. So we know for lag compensation, our beta has to be 1, and this is the transfer function. So in order to improve the steady state error, we will be using lag compensation because it will provide the integrator effect, and that will ensure my steady state error to be whatever desired uh, requirement is there. And that's why we'll be using the lag compensation. And for both the cases, first we have to ensure whether a simple gain K will be sufficient or not. If it is sufficient, that will end the design. But say if it is not sufficient, then we will be designing the lag compensation. So first we'll get the poles and zeros, and then we'll check the final closed loop root locus. Okay. So coming to our question, this question is a little bit tricky. Why? Because I have given both the transient requirements as well as the gain requirements. I mean the steady state error requirements. But the transient requirements doesn't need a lead compensation because a simple gain K is making sure the root locus passes through the closed loop poles. So always in any question, first we have to calculate the closed loop poles. Then we have to check whether the simple gain is sufficient or not. Say if the simple gain K is sufficient, then we don't need any compensation. So in this question, to meet the transient requirements, we will be not needing an additional lead compensation, but a gain is sufficient, which is what I have told here. So now using this gain, I want to see whether the steady state error requirement is also met or not. So I have calculated KV and I have seen that the steady state error requirement is not met, which means that I will be needing compensation to achieve the steady state error, and which compensation will be used to improve the steady state error? Lag compensation. So once we get the lag compensation requirement, then we know that lag compensation transfer function is this. And what we are trying to highly stress more about is, because we are incorporating an additional pole as well as zero, this too should not alter the root locus drastically, because if I am designing a compensator that is changing the root locus, then my transient response is not met. So this poles will not be lying on the root locus. So my designed or the designed compensator, lag compensator, should make sure that this steady state error is met. However, it should not cause any change in the root locus. To be precise, the pole and zero should be close to each other, so that the angle contribution of these compensator pole and zero will be less than 5% when we look towards this pole. So this is a thumb rule that this should be less than 5%. And then my beta is ZC by PC. So my pole PC can be obtained as ZC by beta. So once I get ZC as well as beta, I can get PC. How do I get beta? So beta is corresponding to the additional gain that is needed to achieve the desired kV. So beta is nothing but kV divided by kV obtained. Okay. Once we get this, I got beta. Once I get beta, I need to calculate ZC and PC. But we make an assumption rather than solving it by considering ZC to be 0.1, and then PC can be obtained as ZC by beta. Once you get ZC as well as PC and beta, our transfer function is obtained as S plus ZC by S plus PC. One thing after designing this, you have to make sure is check angle contribution, check that phi is less than 5 degrees. If not, choose another ZC and repeat. Choose another ZC and repeat the process. Yeah. So once this is done, our compensation is done. But we also have to check whether root locus is varied drastically or not. So for that, we always have to check in the MATLAB. So let me quickly explain what we have done in the MATLAB code as well. And I will also be summarizing towards that, which is very important, because if I don't teach everything clearly, you will also be confused, and it will not help you. So I'll towards the end of this session, I will also teach. I should say summarize. I will be summarizing what I have taught today, and then I will also go through the MATLAB code, and then I'll stress on what is important, what are the key takeaways, what are the uh, things that we should bother about in which design, so that things will be more clear. Okay, so guidelines to design the lag compensator. First, I'm clearing these three lines are common for any code. I'll be clearing the command window workspace as well as closing all the plots. Then I have to define the transfer function, which is coming from the input. And then based on the desired specifications, I have checked what are my roots are. Then using these roots, I will plot the root locus and then see whether a gain k is sufficient or not. So that gain k is obtained to be 32.4. Now I have checked the other desired specification, which is 10. So I have calculated kV desired to be 10 because that is given. And then I have calculated kV compensated, uncompensated. Without any compensation, only gain. I have calculated. So if you calculate this and then check kV compensated is coming 1.8514, which is lesser than the desired. So there has to be an additional gain in the system with compensation, like a pole and a zero in the compensation, which will contribute gain. But it should not contribute any phase, because if it contributes phase, that will alter the root locus, and then that will change the or deviate from the desired transient response. So we need to incorporate gain in the system to achieve the desired steady state error without altering the closed loop pole locations, or I would say without altering the root locus plot. So this can be done using the lag compensator, and we have obtained the beta value from this expression, which is kV divided by kV uncompensated, and then ZC is considered to be 0.1. After that, we have to calculate PC. Then we have to see what is the angle contribution, and then from there we can get that the angle contribution, if it is less than 5%, the design is fine. If it is more, then you have to change ZC and then do it again. However, we are not doing that as of now. Sir has shown that it is less than 5%. So zero point 0.1 can be considered as a thumb rule, and then you can start. It's a good value to start the design with. Then I have calculated ZC, sorry, and then the closed loop G closed loop can be obtained as feedback G into GC, and then from this G into GC, now I can get whatever I need, and then I'm plotting the root locus of this G into GC as well, along with G. So I'm plotting the compensated root locus along with the uncompensated root locus to see whether my original root locus is actually deviating or not, because the original root locus is passing through the desired pole location, right? With certain gain, it is passing through that. Now I have incorporated one pole as well as zero in the system. So I want to achieve the desired error without changing the root locus much, because changing the root locus will change the transient response. So I don't want to alter the transient response. However, I want to achieve the desired steady state error. So the GC is trying to achieve that steady state error without changing the pole location. So my root locus should not alter much, which is what again we are getting over here. So there are two root locuses and they are very close to each other, except there is slight difference, which is okay. So my transient response will not be affected that much. However, I am trying to achieve the desired steady state error using this compensation. So this is all about lead as well as lag compensation. Now we'll be going to lead lag compensation. There is less than a minute. If this meeting ends, kindly join back so that we can discuss lead lag compensator. If you have any doubts, you can ask. So if this meeting ends, kindly join back so that we can discuss further. Any doubts? Okay, now we'll move to the final topic of today's discussion, which is lead lag compensation. So when are we going to use this? So the first thing is when we need to meet both the transient response and steady state error requirements. And steady state error requirements. Okay. Because the lead compensator will be used to get the transient response, and lag compensator will be used to achieve the steady state error. So this will be achieved by the lead compensator, and then this will be achieved using the lag compensator. Okay. So now, what is the point here? The transfer function GC of S is nothing but it has single Kc into S plus 1 by tau 1, S plus 1 by alpha tau 1, then S plus 1 by tau 2, S plus 1 by beta tau 2. So first we'll always design the lead compensator. So this is my lead compensator with the gain. And then we'll decide the lag compensator. So we have to design this first. Design this first. Once this is designed, then design this. Okay, once that is designed, then we'll be designing this. So the objective is to check whether always the objective that we have at the beginning is to check whether gain should suffice. So this is point number 3, if I'm not wrong. Yeah. So this is point number 3. So check whether a gain K is sufficient. If it is not sufficient, if not, then design first lead and then lag compensator. Okay, first we'll check the lead compensator, then we'll check the lag compensator. So once that is designed, we are going to design this. So first lead, then lag. And the method remains same. So the individual design criteria or guidelines remain the same. Okay, so this is how we are going to design both lead as well as the lag compensation. So let us consider one example. If you see in this example, I have given again two criterias, but we have to again always check whether the root locus will pass through the desired pole location if we are considering certain gain. So we'll plot the root locus and then see whether it is passing through the desired pole locations or not. Okay, so the first point is MP is equal to 16.3% or its value is 0.163. And then the settling time TS is 4 seconds. So from this, always I will be calculating minus zeta omega n plus or minus omega n into square root of 1 minus zeta square. Again, there is a j that I think I might have forgotten previously. Let me add it if I have missed it. Yeah, I have missed, so I'm using red color. There will be j here. Similarly, I think at the beginning we might have missed it. Yeah, so we have missed j. Because why always J? Because this is a underdamped system for which there will be peak overshoot. If it is not peak overshoot is not, let's say if it is overdamped, then there is no question of peak overshoot. So whenever there is peak overshoot, it means it's an underdamped system and then we'll be getting J. So for this given condition, 16.3 and 4 seconds, I have to see what are the poles, desired closed loop poles and see whether a simple gain is sufficient or not. So let me close this as well as this, and then I'll go to the lead lag compensation code. And then this is my input 10 by S into S plus 1.2 into S plus 6. And then my MP is 0.163 and then TS is 4. So this until here, I'll be calculating the roots. Then after that, first I'll design the lead, then I'll be designing the lag. So what I'll do is I will select till this point and then I'll run it. So these are my roots, -1 plus or minus J 1.7319. So, sorry, minus J 1.7319. Minus J, sorry, -1 plus or minus J 1.7319. So this is my desired pole locations. After this, what I'm doing, -1 plus or minus J 1.7319, I will always plot the root locus of G. So I'll plot the root locus of G and then I will see whether these points are lying on the root locus or not. So let me do that. I can clearly see that root locus is not lying on the desired poles. So root locus is not going through the desired poles, which means I need compensation, which will ensure that root locus passes through the desired poles. So I can say that I have checked the root locus and then root locus is not passing through the desired closed loop poles which says that we need compensation. We need compensation. So again, we'll check what compensation are we going to need, because this is about closed loop poles, which means transient response. We will be needing lead compensation. Lead compensation. So we will see the step-by-step guidelines. Now that we have understood the process and the MATLAB code, I'll be only referring to the MATLAB code so that we can understand the MATLAB code, and theory is always, theory is already told. So for calculating the angles, first we have to calculate phi 42.52. How I have calculated this? So for lead compensation, first we have to see the angle criteria, right? So from the angle criteria, I have to calculate the phi. Yeah. So from this I can get. So my pole locations are 0, -1.2, -6. 0, -1.2, and then -6. 0, minus. I think -1.2 can't be too close to 6. So -1.2, and then -6. And then my desired pole SD is at -1 ± J 1.739. So it is here. So this is SD, and this is at -1. Okay. So what we have to do is we have to calculate the angle. So if I calculate this, if I calculate this, if I calculate this, now I have to see how much is this theta 1, theta 2, minus theta 3. So I have to calculate theta 1 plus theta 2 plus theta 3. So theta 1 plus theta 2 plus theta 3. Basically, minus will be there because it is corresponding to the poles. So minus of theta 1 plus theta 2 plus theta 3 plus phi is equal to 2k plus 1 into 180 degrees. And then if you calculate whatever phi I got, how much it is? Phi I have obtained 42.52 degrees. 42.52 degrees. Phase is needed. Again, just let me see if I made the same mistake in the lead compensation. Lead compensation. So yeah, so here also same, minus of theta 1 plus theta 2 plus 5 is equal to 2k plus 1 into 180 degrees, or 2n plus 1, whatever it is. Based on that, we got it. Okay, we got how much is needed, additional 5. So yeah, where are we? Yeah, we are here. So I got the phi to be 42.52 degrees. So I know phi and I know theta. Theta is cos inverse zeta. Zeta is given. And then gamma, which is important, half into pi minus theta minus phi. So once I know all the angles using the formula that sir has shared, we can calculate ZC of the lead compensator, PC of the lead compensator. I will also get the alpha. Once I get all those things, once I get ZC as well as PC. So if I go here, I can calculate using the formula. So what I can do is I can calculate ZC and PC of lead compensator can be calculated. Lead compensator can be calculated. Once this is calculated, we can get Kc using the angle criteria, using gain criteria. The gain should be 1 there, right? So we can calculate Kc using the gain criteria. So Kc, how do I calculate that point, whatever r of 1? So let me calculate. So we have calculated till there. So now we can calculate till this. Yeah. So if you see as well, it is that closed loop pole, and then at this as well, we are calculating the gain, and then that should be 1. So based on that, I can get Kc. And then if you see my ZC lead, it is this. So ZPK of GC lead is given by this. So this is the gain and these are the pole locations. Now we have to see whether this G into GC lead is sufficient to get the desired gain. So if the gain, so if the gain is met without needing the lag compensator, and then say just with lead compensator is sufficient, then we don't need lag compensator. So what we have to do is, let me go to the next slide. So once this is done, lead compensator is done. Now coming to the lag compensator. So we have to see whether the limit kV of the uncompensated means without lag compensated, uncompensated, which is given by limit s tends to 0, s into GC lead of s into GC of s, whether it is greater than kV, or check this and then check whether this meets the, whether this meets the desired requirement or desired specification. Say this is not met. Say this is not met. Okay. If not, what if not? If not, if it doesn't met, then we will be needing compensation. Compensation is needed. Which compensation? The compensation that will improve the steady state error, which is which is yes, lag compensation. And we know lag compensation beta can be obtained as kV divided by kV uncompensated, and then we can choose ZC of the lag to be 0.1, and then from there I can calculate PC. Once I can get that, I'll have to check the root locus. Once the lag compensation is done, once this is done, once this is done, once design. So I'm writing this in red color because it is critical. Check the root locus. So this has to be checked. Once the compensation is designed, then we have to design the, sorry, once it is designed, we have to check the root locus to check if everything is fine or not. Yeah, so KV desired is 50. And then if we calculate the uncompensated, with like we have the lead compensator, whether the lead compensator and the plant is sufficient or not. I have gotten KV uncompensated to be 1.6223, which is not sufficient. So I will be needing the lag compensator. So I have calculated beta, ZC lag I have calculated, PC lag I have calculated. Again, after this, you have to see, and the angle criteria for this should be less than 50 degrees. But here I have skipped that part. I can get GC lag. So now the overall lead lag compensator is GC lead into GC lag because it is lag lead compensator. And then I can display GC, and after that I can also display the closed loop. And as I have said, I will be plotting the root locus and then seeing the original root locus and the final root locus, and it should pass through these 2 points. So let us run. Yeah, so this is my compensator. 2.9137 into s plus 1266 is by s plus 3.159 is the lead compensator, s plus 0.1 by s plus 0.00324 is the lag compensator, because ZC of the lag is chosen to be 0.1, and then the pole of the lag compensator will be smaller because it will be closer to the imaginary axis. So these two correspond to the lag, and then the other ones corresponds to the lead. And this is the overall closed loop transfer function. Now let us check the root locus. Yes. So if you see very clearly, now this is very interesting, right? So the blue color, so the blue color, so the blue color corresponds to the uncompensated without any compensated. And then one thing I'll do, just a minute. So addition to this, I'll also do G star GC lead. So one is with lead, and one is without anything, and one is including all. Yeah, so now this will be very interesting. Yeah. So I'm interested only in this region. So if you see, yeah. So this is the like interesting aspect. So this blue color that you can see, this blue color corresponds to the original uncompensated. So there is no compensation and the gain is not sufficient because it is not passing through this desired poles. Now, if I consider lead compensation because it is designed to achieve the required transient response, it is passing through the poles, desired poles, but that is not sufficient to achieve the desired steady state error. And again, I need lag compensation, but this lag compensation should not alter the response much. It should not alter the root locus much, which means the transient response. So it should be more or less same and it is more or less close to each other. So this one is the uncompensated. This one is with only lead compensation. This is including all. So as you can see, we are not trying to alter the root locus much, whereas we are trying to achieve the steady state error. So these are not much. Say if you feel the root locus is deviated so much, then what we can do is we can go and then we can choose ZC to be a different value. Say ZC I have considered 0.1. Now I'll consider 0.05, half of that, and then see how it is changing. So now it may be closer, or let us see. So now you can see it is very close. It is better than what we have previously obtained. If you make it closer to the origin, then it will be better. Yeah. So this is all about lead lag compensation. So this is the overall design. So we have understood lead, we have understood lag, and then we have understood lead lag also. So now let me draw the border plot of the lead lag compensation. So you can see the name suggests lead lag doesn't mean the lead part will come first and then the lag part. We are basically designing the lead first and then we are designing the lag. So if you see the border plot here, we can see first the phase is undergoing lag. Why? If you draw the ZPK of GC. So this is the ZPK of GC. So the lead part, or I will do one thing, ZPK of GC lead and then ZPK of GC lag. Yeah, so if you see the lead one are a little bit far away from the origin and the lag one are closer to the origin. And in this, the pole is coming first because it is lag, then the zero, then, sorry, yeah. So first this pole is coming, followed by this zero, then this zero is coming, followed by this pole. So first the, let me go to the border plot. So first the zero, first the pole, then the zero, then the zero, then the pole. So that's why there is a lead, sorry, there is a lag, and then there is a lead. So that's why uh, it is falling first because pole is coming first, followed by two zero. So that's why it is crossing zero and then followed by pole. So that is why it is coming back to zero. So first the lag, then followed by lead. So this is the border diagram. So to quickly summarize today's session, let me go to the page one. Yeah. So to quickly summarize today's session, we have discussed about the design of lead and lag compensation using the root locus. So starting with the lead compensation as well as lag compensation requirements, why it is needed. So lead compensation means the zero will come first, followed by pole, which means zero is closer to the imaginary axis, so it will add a derivative effect. That's why the transient response will be improved. So whenever there is improvement in the transient response requirement, we'll be using lead compensation. And when we'll be using lag compensation, whenever we need a requirement to improve the steady state error. Why? Because the pole will come first, then zero, which means the pole is closer to the imaginary axis, so it will have an integral effect, which will improve the steady state errors. And lead compensation can be given written by this transfer function where alpha will be less than 1, and lag compensation can be written as this transfer function where beta is greater than 1. And then lead lag compensation can be written as this, and alpha is less than 1 and beta is greater than 1, and we are designing both of them independently. And one of the student has asked this question, so that's why I have written this, but this is not part of this week. Then how do we design the lead compensation or lead compensator using root locus? So first we have to always check whether a simple gain is sufficing. And if it suffices from the root locus, we will see that the desired poles will lie on the root locus. If not, then we'll design the lead compensation if it is about transient response. So first we'll have to get the poles and zeros, then we'll calculate the gain from the gain criteria. So the lead compensation here I have given one transient response requirement, and based on that first I have calculated the closed loop poles. And once this is done, I have to plot the root locus and see whether gain k is sufficient or not. And we have obtained that gain k is not sufficient. So we'll be designing the root locus. Sorry, we'll be designing the compensator. And for designing that, first we have to see how much additional phase is needed. And this additional phase is given by phi, and theta is given by cos inverse zeta, and gamma is given by the formula 1 by 2 into pi minus theta minus phi. From there, we'll get theta, gamma, and phi. From there, I can calculate ZC as well as PC. And from the gain criteria, I can obtain the KC. So once we obtain, we have to see whether the transient response is meeting or not, because we should always check at that whether the desired response or the desired requirement is being met or not. Then how do we design using lag compensation? So this is the transfer function for the lag, and this is to improve the steady state error. So first we have to always see whether a simple gain k is sufficient or not. If it is sufficient, then we don't need to design any lag compensation. Else we might have to design, and then first we'll be designing the poles and zeros, and then finally we have to check the root locus, because in the case of lead compensation it is the transient response requirement. Here we are designing the steady state error, but it should not alter the root locus. So that's why we have to plot the root locus and then see. So the lag compensation, here I have given one example where we will be uh, asked to check two requirements. One is the steady state requirement, but transient requirement is also given. So in this problem, we have seen that we have realized just by using simple gain, the root locus is passing through the desired pole. So we need not design the lead compensation. So a gain is sufficient. But whether this gain plus the plant is sufficient to achieve the steady state error, no. Which means we need lag compensation. And for designing the lag compensation, one important thing is it should not contribute much angle to the closed loop pole, so that it will not alter the root locus much. It will have some impact, but it should not have drastic impact. So phi is assumed to be less than 5 degrees, and then ZC is considered to be 0.1, and beta is kV designed by the kV of the uncompensated. And from there, I can calculate the lag compensation transfer function. And once we do, we have to check whether phi is less than 5% or not, which I have skipped just to save some time. And then if not, then we have to choose another ZC and repeat the process. Finally, we have to plot the root locus and check that the root locus is not changed drastically. If we are asked to meet both the requirements, and say the transient response as well as steady state error, and transient response cannot be met by simple gain k, then we have to design both the lead compensator as well as lag compensator. And the lead compensator will be responsible to improve the transient response, and lag compensator will be responsible to improve the steady state error requirement, or improve the steady state error. So first we'll be always designing the lead compensator, and once the lead compensator is designed, we'll check whether the root locus is passing through the designed poles or not, and then we'll see whether that will also meet the steady state error requirement or not. If not, then we'll design the lag compensator, and then again we'll plot the root locus to see that the root locus has not changed much, and then both the design guidelines are met. So here I have considered one final example where I have given the transient requirements as well as the steady state error requirements. And then we have seen that the transient requirement cannot be met by simple gain. So we need compensation, and we'll be plotting that. We'll be designing the lead compensation. And then first we have to check how much phase is needed, and gamma and theta can be obtained using this. And then once I have obtained this, I have calculated both ZC and as well as PC. And then KC, we can use gain criteria. And then once we have designed the lead compensation, we'll see whether this is sufficient to achieve the desired steady state error specifications. If it is not achieving, then we need compensation. Again, which compensation? Lag compensation. Once the lag compensation is designed, we have to check the root locus. So for the same, I have given 3 codes today, and then common codes are Bode plot and root locus, which we have discussed in the previous week. But anyway, I'll be uploading these codes as well. So I'll start with lead compensation. I'll close others. Yeah. So in the lead compensation, first I'm defining the transfer function and the desired specifications, which will give me the roots. Then angle I have to calculate from the angle criteria, how much angle is needed, and theta and gamma can be obtained using these formulas. Once I get all the angles, then I can calculate ZC, PC, and from there I can calculate the alpha as well. But for calculating Kc, I need to use the gain criteria, which I can obtain from this. And once Kc, Zc, Pc are obtained, I'll calculate the closed loop transfer function and the desired transfer function, and then see whether the step response is matching or not. And then if we do, for this case, it is perfectly matching. So that is all about the lead compensation. Coming to lag compensation, again, the starting code lines of code will be same, where we are defining the transfer function, and then we are getting the desired pole location, and then we are seeing whether root locus is passing through this. If not, then we will be needing uh, lead compensation. But if it is passing, in this case it is passing, then we have to see whether the steady state error criteria is met or not. If not, we have to calculate kv uncompensated, and kv desired is given, and the beta can be calculated from this gain, and zc is assumed to be 0.1, and pc is calculated from that, and then we are checking whether the root locus is closer or whether it is deviating much. So we have seen that in this case the root locus is uh, closer to the desired pole location, so this design criteria is fine. Then coming to lead lag compensation. So in this case, a simple gain will not meet the transient requirements. So again, we have defined the transfer function and the desired pole locations. And then first we have to design the lead lag lead compensator. So first I have calculated the angles. Again, this is coming from the angle criteria, theta and gamma formula. And then first I have designed the lead compensator by calculating ZC lead, PC lead, and alpha. Then KC can be obtained from the gain criteria. I have obtained GC lead. Then I have seen whether this KV uncompensated will meet the given steady state error requirement, and I have seen it is not. So I have to design the lag compensator as well. And once we design the lag compensator, then I can get the closed loop transfer function if I need. And I'm plotting the root locus of all three, and then checking whether the root locus is varying much or not. So these are the three lines. If you zoom in, so this one with and without lag, the root locus change is not drastic, and this is with uncompensated, so my design is met. So in this way we design lead and lag compensation using root locus. But we will see in the upcoming session, which is on Monday, that this uh, method can be made much simpler using the frequency response or the Bode plot method. So that's all about today. If you have any questions, you can ask. If no, then we'll again be meeting on Monday, and where I'll be discussing the design criteria using the Bode plot method. So if you have any queries, you can ask, else we can end this session. Any questions? Okay. If no, then I'll wind this end this session today here, and we'll be again meeting on Monday, where we'll be discussing the design criteria for designing the lead as well as lag compensators using the Bode plot. So that will be also very interesting, and I'll also be showing the MATLAB simulation, so we can correlate both theory as well as the simulation. And I wish you all the best for your week 8 as well as 7 assignments. And again, I'll be meeting you on Monday with week 9. So with that being said, I'll end this session here. All the best for your assignments. See you on Monday.